Welcome to the explanation of the Chapter 7 test review for advanced geometry. So again, as we go through the answer key and review, I'll try to explain some of the thought processes behind the answers that you can't really see on paper. And again, during Wednesday's class, we can cover any additional questions people may have before the upcoming test. So the first section, we're thinking about our triangle congruence theorems. So we have our side, 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 angle, side, angle, our side, side, angle, as long as the larger side is opposite the larger angle, and our hypotenuse leg. So if we look at the first triangle here, we have sides of 5, 6, and 8 on both triangles. So we have side, side, side congruence. And when we are writing our congruence statement, so a congruence statement is this part here, stating that triangle MPS is congruent to triangle BRJ. You want to make sure, again, you match up corresponding parts. So the order of these three letters, as long as they're consecutive, doesn't matter as long as the corresponding parts match with the other triangle. So M matches with B, P matches with R, S matches with J. In our second example, or our second problem, we have a shared side here of TN, so I drew in the congruence there. Then we have our 90-degree angles of N and T, which are congruent, and then we know side TP is congruent to MN. So in that case, we have side angle, side congruence, and its triangle NMT is congruent to triangle TPN. Again, you can change this order as long as the corresponding letters match up. So N with T, M with P, T with N. And in our final problem in this section, problem number 3, what we were given was the vertical angles here at O. So we know those are congruent. And then we were also given these two different sides. So we do have a side-side angle condition, but without knowing that TP is greater than TO or SV is greater than VO, we do not have enough information to say they're for sure congruent. So no, but if we were told this scenario, then we could use side-side angle. But without knowing that, this answer would be no. So the process for number 4, sketch triangle ABC, where angle C is 106 degrees, side AC is 2 centimeters, and AB is 2.8 centimeters. Will all triangles with these given measures be congruent? If so, what theorem proves it? So when I drew this, I started with side AC. So I first drew my 2 centimeter segment here. Then I set my protractor at point C, measured to 106 degrees, because we want the 106 on the interior. And then I put a mark up here where I knew 106 degrees was. I just drew that line all the way to that mark. And then to figure out where to place B, I set my ruler at point A, shifted it until the 2.8 centimeters hit this line for C, and that is where I knew to put point B. So then in this case, we have again a side-side angle condition. So what we want to do is check for side-side angle congruence. And again, the way that side-side angle congruence works is if the larger side is opposite the given angle, then all those triangles are congruent. So in this case, our longer side of 2.8 is the one opposite the given angle. So yes, we can use side-side angle congruence theorem, so all other triangles with this measurement would be congruent. If we look at number 5, it says, is the quadrilateral at the right a parallelogram based on the given information? So this is where you'd want to look at 7.8 notes to help you with this, and different conditions or are sufficient conditions for parallelograms. If we look at part A, we were given that DF and CG are both parallel and congruent. So it's a pair of opposite sides, both parallel and congruent, being condition A. So yes, that is a parallelogram. Simply knowing DG and CF are congruent, so we know the diagonals are congruent, that still is not enough information to know if it's a parallelogram or some other quadrilaterals with that property. So that answer would be no. And in part C, DE and GE are congruent, as well as CE and FE are congruent. So in that case, that tells us the diagonals bisect each other, which is condition C. So yes, that would be a parallelogram. Now looking at numbers 6, 7, and 8. It says only the diagonals of quadrilateral ABCD are shown. What is the most specific name for the figure? So this is where you'd want to look at section 7.9. And when I did these 3 problems, I used the hierarchy located in the notes. The 3 paragraphs at the beginning also would be a good resource. So looking at this first diagram, we knew, and I just named my center point E. So we knew AE, EB, DE, and EC are all congruent. So not only do I know the diagonals are congruent, but I also know that the diagonals in this case bisect each other, and the corresponding parts are congruent. So looking at the hierarchy, where diagonals are congruent and the diagonals bisect each other, moving down, what shares both those properties would be a rectangle. Looking at our second example here, so in number 7, we know one diagonal is the perpendicular bisector of the other, 90-degree angle, and this one's cut into 2 congruent parts. And we also know the diagonals bisect each other because this one also is split into 2 congruent parts. So again, we'd look at the hierarchy, see where to start with these 2 different properties, and move down to the quadrilateral that shares them both, which would be the rhombus. And for number 8, looking at this diagram, I know both parts of the diagonals are congruent, so meaning the corresponding parts of AE and EB are congruent, and DE and EC are congruent. So in that case, that would be the property of an isosceles trapezoid. So again, my recommendation would be, when looking at these types of diagrams, use the hierarchy from 7.9. In number 9, we were told that DEFG is a parallelogram. And then it went on to give us many different measurements. So beginning with ED, if we knew ED was 4, we know the opposite side, FG, is also 4. So we could say FG equals 4. Then they gave us the top, EF was 4.5. So the bottom, DG, is also 4.5. Then they gave us DH being 3.7. So the other part of that diagonal is also 3.7. So FH is 3.7. Then they gave us EH being 2.1. And again, we know in a parallelogram, diagonals bisect each other. So segment HG is also 2.1. And then we know opposite angles are congruent. So if they gave us angle EDG, this bottom left corner, then angle EFG is also 60 degrees. And then we know that consecutive angles or adjacent angles are supplementary, meaning they add to 180. So if I do 180 minus 60, I know this bottom right angle of angle DGF and this upper left angle of DEF are both 120 degrees. Then number 10, we were given that segment AT is congruent to AR and angle VTA is congruent to angle VRA. So I looked at these overlapping triangle diagrams. I saw my final goal was to prove RAS was congruent to TAW. So to make life a little bit easier, I just pulled out and redrew roughly triangle RAS and TAW. But you can see I also marked in the original diagram what I knew and added to the diagram as I went. So looking at our table, conclusion was given, justification given. Then we needed to find another shared part that we knew that was congruent. Well, angle A right here was shared by both triangles. So angle SAR is congruent to angle WAT by the reflexive property of congruence. Even though it's named with different points, it's still the same angle, so it's a reflexive property. Then in this case, on each triangle, as you can see, we have angle, side, angle, angle, side, angle. So corresponding parts were already matched up for us. And our justification would be angle, side, angle congruence theorem. Now in number 11, right away with number 2 here, I would encourage to make this more specific and rewrite this as the definition of an isosceles trapezoid. The reason we want that to be more specific is that also allows us to say some angle relationships. So going back, we were given that MRPB is an isosceles trapezoid with legs RP and MB. So just restate the given for step 1. Then using the definition of an isosceles trapezoid, we can identify many other corresponding parts. We know in an isosceles trapezoid by definition, and any trapezoid, our legs are congruent. So we know RP is congruent to MB. Then because it's an isosceles trapezoid, we know that the diagonals, the corresponding parts are congruent, meaning BS is congruent to SP and RS is congruent to SM. So those both stated here. And then also with it being an isosceles trapezoid, we know that our base angles are also congruent. So in this case, I can say that angle MBP is congruent to angle RPB right there, and all of that comes from the definition of an isosceles trapezoid. And then for step 3, I just rewrote it because I ran out of space here. For step 3, I'm going to look at, again, my final goal is to prove these angles are congruent. So anywhere that I can prove corresponding triangles, I can use my corresponding angles. Now, we were stuck going toward the proof with what they were giving us. If I were to work this differently, I would have used a different theorem, but in this case, again, we're going with what they gave us. So in this case, I have to think, how can I get to this triangle, MBP, matching triangle RPB? Well, when I look at my diagrams at this point, what I was missing was the shared side of BP. So I could say side BP was congruent to side BP from the reflexive property. Then triangles MBP and RPB are side angle side congruence because we have the shared side here, we have our angle here, and then we have our side here. Same thing on our other one, side, angle, side. So then once we've proven our triangles are congruent, the next step then is using corresponding parts of congruent figures theorem to state any of our corresponding parts. In this case, angle PMB was congruent to angle BRP.